My distinct pleasure to introduce, I believe, our last seminar speaker for this quarter, the winter quarter, Professor Ricardo Vinuesa from University of Michigan. So Ricardo has been a great collaborator for a long time. He is one of the world's leading experts in high-fidelity numerical simulations of fluid flows, modern methods in machine learning and AI for complex systems in general, but especially explainable AI for fluid systems, and advanced flow control using reinforcement learning. So really high-end fluid dynamics and machine learning brought together for some of the most impressive demonstrations in the field. Ricardo just joined us in the US. He was a professor at KTH in Stockholm for a while, and recently moved to University of Michigan maybe 6 months ago, so fairly recent. But we're doing a lot of collaboration, so hopefully you all get some ideas and meet with and chat with Ricardo afterward. So thank you so much for being here. Really a pleasure to hear your research.
Thank you very much, Steve, for the introduction. You're always too kind when you introduce me, but I appreciate it. And also, it's a great pleasure to be here. I'm very excited to be in Seattle, in a real Seattle day, because last time I was here, it was nice and sunny. This is more the real Seattle. Thank you so much. So yes, I'm going to be talking about a couple of things. One is flow control and how can we use ideas from explainable deep learning and reinforcement learning to improve control, and in particular turbulent control. And then I'm going to be showing some of the methods that we're developing within foundation models and agentic systems for discovery, something that we think can be really influential in the next year, driving discovery, science of the mechanic, and beyond. So let me start by acknowledging my collaborators who have really made this possible over the years. And Steve is one of my top collaborators, and many of the things that I'm going to be discussing today, many students, researchers all over the years who have really helped to make this possible. So really a big thank you to all of them. And also, I want to show you a visualization illustrating some of the very high fidelity simulation data that we have been using over the years. So this is essentially a DNS. It's a NACA 0012 with a rounded wingtip, which means that you have the wingtip vortex and a bit more complexity than you would have otherwise. I'm showing you here vortices of vertical motions. The Reynolds number is 200,000, 5-degree angle of attack. This is about 2 billion grid points. So this is a quite large simulation using a spectral element method. And we also use adaptive mesh refinement to make sure that the details around the wingtip edge are properly captured in our very highly resolved simulations. You can see here the turbulent boundary layer on the section side and how the wingtip vortex basically rolls around the wingtip, impacting the boundary layer here. So we have a strong span-wise pressure gradient that is leading to some local relaminarization, and also how the wingtip vortex rotation is essentially pushing the wake down. And when the wake is pushed down, you basically have an additional component of the drag, which is the lift-induced contribution. So this data set really allowed us to understand in quite some depth, not only turbulence, but also how turbulence interacts with other phenomena like wingtip vortices, three-dimensionality, wakes, and beyond. And this data was obtained by Sebastosi, who was in my group a couple of years ago, Spanish and JFM. We have a lot of high fidelity data on wings of different levels of fidelity. And one note that I want to leave you here, I'm showing you vortices. The vortices are usually shown when people try to show you a nice visualization. They give you an idea of the chaotic behavior of turbulent flows, but there may be other ways to understand turbulence from a visual point of view and from a structure point of view that can help us to get some insight. So for now, just keep an eye on this coherence. So all these vortices show you certain coherence in the flow, which is, together with the chaotic behavior, one of the very important parameters of turbulence. So we are really using quite some high fidelity data to understand these complex flows. And the two main themes on explainability and control and foundation models for discovery and optimization will be connected at the end. So if we start to think about flow control, one possibility to control the flow, if we look at coherent motions, turbulent behavior, what I showed you in the video, one possibility could be to first identify what are the most important mechanisms in my flow. So highlight the most important regions. And here importance is defined with respect to some target. So it could be drug reduction, it could be mixing, it could be reduced acoustic. So for some target, I identify the most important features, which I highlight here in red. And then what I could do is try to target those structures in a very surgical way and nothing else. So if I want to reduce drug, I may want to minimize the structures responsible for drug. If I want to enhance mixing, I may want to increase the presence of those structures in my flow. And how can I affect those structures? That's through active flow control, which I will be talking about later. So how do I identify important mechanisms in my system? We've been using this explainable deep learning framework for a while, but this is not the only way to assess importance. One way to look at this question of what's important in turbulence has been put forward by Javier Jimenez in Spain. He does this in an intrusive manner, basically introducing perturbations in my flow field and reintegrating the governing equations, so basically redoing the DNS, and then looking at what are the perturbations that grow the most. And in this way, one can get one measure of importance in my system. Another approach by Adriano Zano-Duran, who is another close collaborator of Steve and mine at Caltech. So they do causality and information theory. So in this example, for example, what they do is that they decompose their problem into time series with some modal analysis. And then what they do is that they remove the information from one time series and assess what's the effect of that removal in the prediction of the other time series, therefore creating these causality maps that allow us to assess the system in a non-intrusive way. So you are not reintegrating the governing equations, you're just post-processing data and seeing how the different quantities are connected in this a posteriori assessment. What we propose is a bit in between, is something that is intrusive but on a surrogate model and is based on explainability. So the first step is basically to create a surrogate model connecting an input and an output. And this work was developed mostly by Andrés Cremades, who was a postdoc in my group for a while in Sweden, and now he's a professor in Spain. We published 2 Nature Communications studies in the last 2 years on how to use some of these ideas for fundamental studies of turbulence. And in a nutshell, the method is as follows. In my input, I would have basically my information for which I want to identify the important structures. In our case, it would be the fluctuations of U, V, and W now, so 3-dimensional fields of fluctuations. And in my output, I'm going to have the fluctuations of U, V, and W in the future. Okay? This has 2 purposes. The first one is to kind of mimic what Jimenez and Lozano-Duran did about importance in the context of forecasting, but also because we want to use this to reduce drag. And of course, an important contributor to the drag, in particular the friction drag, is turbulence. So if I identify what are the mechanisms that sustain the turbulence fluctuations, I might be able to affect quite significantly the drag. So I have a time delay between the input and the output of 5 viscous units. This was determined based on the time scales of the near wall region. Our results are very robust across a range from 1 to 10 viscous units, which basically indicates that what we identify is, well, it's representative of the near wall dynamics and not so dependent on the actual time step, but the range of time steps. And that interval, this lag is very common in causal analysis. You basically need to identify a time interval characteristic of the physics that you're trying to analyze. So in our case, the near wall region, few viscous units, that's the lag that we consider in our causal analysis. And then we train a deep learning model. In our case, it's a UNet, but we have done this with diffusion models as well, connecting the input and the output. Our predictions have 0.5% error, so they're very accurate. And once that model is trained, I use a game theoretic algorithm called SHAP, which stands for Shapley Additive Explanations, which in a nutshell, what it does is remove information point by point from the input. So if I remove this pixel and I repeat my prediction, if the prediction error increases significantly, that means that this information was very important. If the prediction error does not change much, that means that that information contained in that pixel was not very important. Okay, and I oversimplified things a little bit here. If you're curious about the method, we can talk more about it at the end. But in a nutshell, that's what we are doing. And doing this approach, I have for each instantaneous flow field a three-dimensional distribution of importance, which we can then analyze. And through percolation analysis, I can identify coherent motions based on importance. Okay? So I can identify three-dimensional volumes of very high importance in comparison with other classically studied structures in turbulence. Vortices is what I showed you in the video. And you can see that they're actually very different from what we are identifying as being important. So you can start to think that maybe vortices, at least for this target, might not be the most relevant. These over here are the Reynolds stresses or intense Q events. Those ones look a bit like the sharp structures, actually, at least visually. And here at the bottom, I'm showing you the streaks, which, as we know, or as is known in the classical literature of turbulence, they play a key role in the near-world production of turbulence. So what we did was to try to compare these types of structures first from a statistical point of view. So basically looking at the joint probability density function. So statistically, what are the properties of each type of structure? On the left, in this big panel, I'm showing you the PDF of the sharp structures, where the vertical axis is the inner scale wall normal distance. The horizontal axis is the inner scale stringwise velocity. And here you have basically the PDF. So I'm comparing the map from the sharp structures, the most important features in my system, with the three classical ones. These are Reynolds stresses, streaks, and vortices. And you can see that there is some similarity. For example, if you look here, this region looks a lot like that one. These are regions of positive stringwise velocity close to the wall. Those are actually streaks, and they are very well known in the turbulence literature. These ones over here have negative stringwise velocity, and they're far away from the wall. They look a lot like these, which are basically ejections. And if we keep looking, we actually find here at y plus 15 quite good agreement between these two regions and those ones over there. These are the very well-known low speed and high speed streaks. So again, the streaks are very well known in the turbulence literature to be important in the generation of turbulence, in the production of turbulence. And also with the vortices, there is a bit of agreement here at the channel center, as you can see in this comparison over here. So this is the statistical comparison. What we also wanted to do is go to each instantaneous flow field and compare the structures and see what is the percentage of volumetric agreement between the classical ones and the ones that we have defined purely based on importance. And what is interesting, so here I'm showing you in the vertical axis the percentage of agreement, and the horizontal axis the wall normal distance. What you see in this yellow line is the agreement between streaks and sharp. So the sharp is the importance-based structures. And if a classical one agrees with ours, that means that it's important for this metric that we are defining, because ours are basically the definition of the important regions for that metric. And you can see that the agreement is about 90% at y plus 15, and that agreement goes down to 0 everywhere else, which is actually consistent with the classical knowledge. The streaks are prominent at y plus 15. That's where they are responsible for production, and that's where they agree with our important regions. But the other structures have different agreements in different places. The Reynolds stresses have quite some agreement, about 50% close to the wall. Those are the sweeps. And about 60% far away from the wall. Those are the ejections. And the vortices only agree about 15% at the channel center. So this basically shows that the classically studied structures only paint a partial picture of wall-bounded turbulence. And in fact, every time that people do a nice CFD simulation and they show up visualization, they typically show vortices, because that's kind of like one of the most natural things to define in turbulence. They are eddies. We associate the structures with eddies. But for this particular target of sustaining the fluctuations, the vortices are actually not very important. So this kind of shows that sometimes the physical bias that we have going into a problem, the fact that you can see something does not mean that it's important. Sometimes it's actually interesting to interrogate the data in a physics agnostic way and let the data tell you what's important and what is not. In other words, this is a bit the story of the three blind men and the elephant. Sorry for the people in the session before, they have to see this again. But basically, you know that three blind men are asked to describe what is an elephant. The first one says that an elephant is a snake because they're touching the trunk of the elephant. The second one says that it's a wall, and the third one says that it's a rope. That's basically an example of partial information, right? And none of them is technically wrong, but none of them is telling you the whole story. And that's a little bit what we see with the classical structures. They're only looking at importance for part of the events that matter for a whole turbulent flow. So this is about what we have been using and developing with importance-based explanations in world-bounded turbulence. And once we identify what's important in my system, then I can try to control those things. And to do that, we have been using deep reinforcement learning. So we were quite pioneering on using reinforcement learning for turbulence control. So we basically, this is a primary, small summary of what reinforcement learning is doing, although I guess in here, mostly everybody knows about it. So you have an agent interacting with an environment, which is our free flow system, either through an experiment or through a simulation. That interaction is through actions, which are essentially, in our case, blowing and suction. So we're going to consider active flow control with jets on the surface that are sometimes going to blow air and sometimes they're going to suck air. Those actions are changing the state of the system, which is our observation of the system. And they're also changing the reward. And the reward is a measure of the quality of those actions under a certain norm. So the idea is that this is trained stochastically, such that we are rewarding the actions that allow us to increase the reward. And once we train this system, then this is evaluated deterministically in such a way that a policy pi is created where, given the state of the system, we will receive the actions to take in order to maximize the reward. And this was work done a lot by Luca Bastoni at the beginning, who was a PhD student in my group. Now he's a postdoc in Munich. He did fantastic work on this. And you can have here a review paper on reinforcement learning and control for many applications in fluid mechanics. So that's kind of like the main idea. We consider turbulent open channel flow as a benchmark. This is a channel with a single wall. At the upper boundary, we have a symmetry condition, simply to simplify a bit the control implementation. The results with two walls are identical. In terms of the control performance, the flow is a bit different, but the control performance is the same. And this is at Arita 180, which is a low Reynolds number, but turbulent, where we consider both a minimal and a full channel. And our classical comparison, our classical benchmark is opposition control, which is described here. This is a method that is 30 years old. It's essentially a linear proportional control. So if this is your wall, you will sense above the wall, typically pi plus 15, the vertical fluctuations. And in opposition control, if you have a positive B fluctuation, you do suction. If you have a negative fluctuation, you do blowing. So basically, it's a linear proportional control trying to cancel out those vertical fluctuations. Which, of course, I mean, it works well, but one could expect that maybe through reinforcement learning, we can learn a much more sophisticated mapping between the state and the action than simply a linear control. And that's a little bit what we try to do with our framework for multi-agent reinforcement learning training. So one of the keys to control turbulent flows where the dimensionality of the system is very high is to parallelize the training. So reinforcement learning works through gathering experiences, and that's very expensive. It is not very sample efficient. You need to run many simulations to expose your agent to enough situations such that you can train and learn what are the policies that work best. And that's, of course, very expensive. But what we did here, and this is work that we published also with Steve in Nature Reviews Physics, this is an experimental implementation, is the following. So if you have a turbulent channel where you have two homogeneous directions, the flow is periodic in the stringwise and spanwise directions, that means that each of these blocks, each of these field environments is seeing a different instantaneous realization of your flow, because you have your turbulence doing different things in different places, as you saw in the video. But because the flow is homogeneous in both directions, the statistics are the same. The flow is homogeneous. So each of those points, if you average for long enough, will give you the same statistics. So in essence, what we're having here is a bunch of different regions with different observations of the same statistical problem. So that's one key. The other key is that all these pseudo environments share the same parameters, so the agent is the same. So now we have the same agent with the same parameters, seeing a lot of simultaneous realizations such that we can really accelerate the training. Now we are 16 times faster. We don't need to run 16 simulations. Just in one, we encapsulate 16 different experiences to be able to train our reinforcement learning algorithm. And the other key here is that all the pseudo environments share a common reward, in this case, drag reduction, which means that the agents start to cooperate. So I don't have each individual region trying to selfishly optimize the local environment. All of them try to cooperate to achieve the overall highest reward, which is the drag reduction. And those two things were the key to be able to unlock the application of reinforcement learning to higher Reynolds number to confluence. So the performance here, where the reward is the friction reduction in a turbulent channel, and these results were by Luca 3 years ago. The reinforcement learning gives me 30% drag reduction. The opposition control, which is the linear traditional method, only 20%. So we can do significantly better than opposition control by coming up with a policy that is going to be something much more sophisticated than simply linearly opposing the fluctuations. So this is a huge improvement. But more interestingly, can we come up with a better reward to train the reinforcement learning? I told you at the beginning that we want to identify what's important and use that to guide my optimization, my training of my agent. And this is work that we did with Miguel Benitez, who was also a postdoc in my group. Now he's faculty, he's a professor in Manchester. Andres Cremades was also here, and Luca was also here. Everybody was involved in this study. And we're going to compare for the same setup to a channel flow where we temp at wave at 15 and we do blowing and traction at the wall, different rewards. In red, the naive drag reduction. So the reward is to reduce drag, which is the 30% that I showed you before. In green, I'm going to show you what happens if the reward is to minimize the Reynolds stresses. In red, to minimize the streaks. And in purple, to minimize the shock. So to minimize the most important structure in the flow. And this is what the results look like. What I'm showing you here is drag reduction as a function of time. In orange, you have the curve that I showed you before, reinforcement learning for friction. That's 30% drag reduction. And you can see that it has quite some oscillations. In purple over here, you can see the reinforcement learning for SHAP for the most important structures, and that's 5% better. You can see that the line is above the orange one. And also, the oscillations are much lower. Right? So this kind of shows that the drag is, in this case, the symptom, and the reinforcement learning for drag is, treating the symptom, whereas the SHAP is identifying the underlying disease, the underlying root cause of that symptom, which are the important structures responsible for the drag. So in the purple line, in the SHAP, what we do is that we have a much more surgical approach. We're targeting the mechanisms and not the output of those mechanisms in my control. In reality, what happens with the reinforcement learning for friction is that we learn a bang-bang control. So basically, it's trying to destabilize all the near wall region, whereas the reinforcement learning for SHAP is just destabilizing certain structures that are key in the near wall region. That's why it has lower oscillations and it achieves better performance. This figure also shows an interesting result. When we minimize the Reynolds shear stress and the streaks, we get worse performance, which basically confirms that the SHAP structures are actually the most important. Because when we inhibit their presence in the flow, we get the highest impact in drag and turbulence features in our. But this kind of confirms that our SHAP analysis makes sense, and also confirms our hypothesis that guiding the reinforcement learning algorithm through explainability could be potentially a good idea. In fact, here I'm showing you the cost of the control, which is measured by the momentum that is injected or sucked from the system from my actuators. And the orange line is the reinforcement learning for friction. The purple line is the reinforcement learning for SHAP. You can see that this is basically half. So we have, again, a much more efficient control, which is consistent with the fact that we identify the mechanism and not the symptom. And here, this quantity here is the net energy saving, which is basically the drag reduction minus the power input. And so I need to discount how much power I put in my actuators to achieve that drag reduction. Then the difference between reinforcement learning for shock and reinforcement learning for drag increases to 5.4%. So because the reinforcement learning for friction is more expensive, when I take the cost into account, that improvement from the reinforcement learning for shock gets higher. So this is something that is quite exciting because it allows you to really direct the training and constrain in a way the space that is explored by the reinforcement learning algorithm in order to achieve better performing pulses. And of course, at the beginning, I showed you a very nice wing visualization, and then I've been doing everything now with the channels, so I don't want to disappoint you. We're going to do some things on wings as well. This is a DNS that we did now 8 years ago. This is a NACA 4412 wing section. This is periodic, so it doesn't have the wing tip. This is a span-wise uniform, but you can see that the streamwise development is consistent with that of a NACA wing. Average pressure gradients, a strong migration of near wall turbulence from the wall to the outer region. And the idea is that if we try to use reinforcement learning to control this system, well, it's not so easy, right? Things are not so easy. Here, I'm not going to be using SHAP. I'm just going to target drag directly. And this was worked together with my students, Junin Wan and Paul Suarez, who have also been very involved in the hydrogym environment with Steve. So many of these ideas now are part also of the hydrogym environment. And then I remember one day that Junin came with the first results of implementing the reinforcement learning on the wing. And I realized how expensive that was. And I realized that I needed 3 PhDs, one after the next one, to finish the training. I mean, that would not be feasible, right? We had to do something else. Because of the reason that I mentioned before, this is very high dimensional. Of course, the boundary layer is developing, right, in the stringwise direction, which means that I only have one homogeneous direction, the spanwise, and I have fewer parallel agents to learn in parallel, right? In the channel, I have 2 directions. Here, I only have 1. And the other thing is, if I train here, I still need to simulate the whole wing, and I have very small scales here in the leading edge that are limiting my time step. So I basically get limited by the very small time step of scales that I don't care about for my training. And the other problem is that, of course, simulating wings is expensive, much more than simulating channels, because you have 2 boundary layers, you have the wake, you have the far field. This is a much more complex setup compared with a 2-direction. So then I had this idea. So what if instead of going directly for the wing, we take the NACA 4412 and we split into different blocks, into different regions, and then I do the following. I take this region here, I take its average Reynolds theta, which basically gives us an idea of the bulk properties in that region, and I define a channel flow, which can be as big as I want, with as many pseudo environments as I want, and I adjust my Reynolds bulk, so basically my streamwise pressure gradient, to match the same Reynolds theta that I have on the wing. So locally in the channel, I have the same properties. Of course, the channel, we are assuming a locally parallel flow assumption, but we are in a way encapsulating the properties of that region of the wing on a channel. And then I do my training on this channel and see if deploying this agent that was trained on the channel directly on the wing would work. And this is beneficial from several points of view. The first one is the channel. Of course, I have 2 homogeneous directions, and I can make it as big as I want. So in principle, I have 20 times more pseudo environments in the channel than in the wing, which means that I'm going to be 20 times faster with my training. Also, here, I take this portion of the wing and I define my channel based on these scales. So I only simulate the time scales that are relevant for that region. I don't care about the small time scales here, which means that my simulation can have a much higher time step because I only focus on the large scales on that part of the domain. And that gives me a factor of 3 more because my time step can be 3 times larger simulating only that region. This means that in terms of time, I'm actually 60 times faster, 60, using my channel as a surrogate to train my model, a sandbox, if you wish, and then plugging that back into my wing. And in terms of cost, because the wing has 176 times more green points than the channel, that means that the computational cost of training on the channel is 10,500 times lower than training directly on the wing. Because again, I've trained much faster and I don't need to simulate the whole wing all the time. I just simulate this very simple channel and that's it. So that was kind of like the idea. We were very, very happy to see that it worked. So this is a NACA 4412. We identified 4 different regions. Of course, the granularity here can be chosen in different ways. We can have more or less regions. We basically looked at the pressure gradient curve and kind of found 4 different regions based on how intense the pressure gradient was. So that means that we trained 4 different channel flows using those local properties in those regions, adjusting the pressure gradient to match the Reynolds theta. And then those 4 different agents trained on 4 channels were put together on the wing. And what we found was the following. On the left, I'm showing you the skin friction coefficient. In terms of friction reduction, we actually get 32%, and opposition control, which is the linear benchmark, only 20%. So interestingly, we get on the wing the same performance that we got in the channel. If you remember when I showed you the channel, this is not with SHAP, and this is directly for friction. I have 30 versus 20, and we almost lose no performance by going back to the wing, which is to me quite cool in terms of how well we can. This is what we call the zero shot generalization, because we don't do any training on the wing whatsoever. All the training is done on the channel. In terms of drag reduction, here you have the reduction of friction drag and total drag. And remember, this is evaluated only on the control region. Of course, the lift and drag are evaluated on the whole wing, where we get 6% drag reduction compared with only 5 from opposition control, which is a pretty cool result. Another application is a case where the stream waist pressure gradient doesn't grow so quickly. It's a NACA 0012, Reynolds number 200,000, 0 degrees angle of attack, so no camber and no angle of attack, which means that you have a pressure gradient, but it's quite mild. So what happens if we so for this case, we didn't train anything. We just took the first region here, this first agent, which in Reynolds number was kind of close to that of the NACA, and we put it for the whole section side of the NACA. So nothing else. And the results were actually quite impressive. We get almost 40% friction reduction, and the opposition control only has 26. And if we look at the aerodynamics of the section, we get 11% total drag reduction and 15% friction reduction. So once again, and this is an even more impressive case because here we haven't trained anything matching the properties of the NACA. This was a completely different agent that we put here, and the performance was even better. This was actually pretty cool. And this is one of the cases that is in Hydrogen's environment, but this is something that is already implemented there. There is another case, this is actually quite new, so with respect to last week, so I don't think you guys have seen this. Because, let me go back to the NACA 4412. What happens here is I have a massive reduction of the friction, but in terms of drag, I have a very good reduction, but not so much. And that's because I am increasing the pressure drag a bit, right? So I reduce the friction significantly by tackling turbulence, but I am increasing the size of the band layer and the size of the wake, which basically gives you more pressure drag. So then the idea that I had was, let's go back to the NACA 4412 and then do the following. We are going to take the NACA. We're going to do, first of all, uniform suction on the whole suction side. So all the jets are going to pull down. Okay, uniform, so no, this is an open loop control. And what happens when you do uniform suction is basically 2 things. The first one, you're inhibiting a bit turbulence because you're affecting the near wall dynamics. You are reducing the pressure drag because when you pull down the boundary layer, the wake is thinner, so you have less pressure drag, but you increase significantly the friction drag. By compressing the boundary layer, the velocity gradient close to the wall increases. So this type of control reduces pressure drag and increases friction drag. Okay, so we first reduce the pressure drag, and then for this wing with the reduced pressure drag, we retrain on 4 channels, 1, 2, 3, and 4, with the new conditions. So we have now different Reynolds numbers on each of these regions, and I add another iteration to this. I not only match the Reynolds theta, I also match the shape factor. Because now, this is a much less canonical case with suction and pressure gradients. And to change the shape factor, we use something called body force damping, which is essentially a body force that we introduce in our channel simulation, inhibiting some of the near wall fluctuations, which is what happens when you do suction. When you do suction, you introduce a strong favorable pressure gradient, you inhibit the near wall fluctuations. So now I'm matching in my channel for each of these 4 regions, not only the Reynolds theta, but also the shape factor. And I train my channel and I put it back into this wing. I have 4 different channels with 4 different agents that I deploy with 0 short evaluation. And now my drag reduction is 10%. So if you remember, when I go to the NACA 4412, I had only 6% drag reduction, because even if I reduce massively the friction, I was increasing the pressure drag. Now I make sure that I reduce the pressure drag and maintain the suction. And when I add the reinforcement learning, train on the channels, 1, 2, 3, 4, that's on top of the section. So I'm actively reducing the thickness of the boundary layer, and then through the reinforcement learning, controlling the turbulence, which is already modified. But the cool thing is that I could reproduce in my channel that modified turbulence through the body force damping. So I could mimic in my channel conditions, not exactly the same, but representative of that new wing scenario, and go from 6% drag reduction to 10% drag reduction in this new setup. And the opposition control also got better, because by actively reducing the pressure drag, then it could focus on the friction reduction, but I'm still doing, well, significantly better than the opposition control. So that's actually quite promising. And of course, one idea of this is that you could potentially come up with very complex geometries and train a whole library of agents on very simple channel flows, mimicking the local pressure gradient, shape factor, span-wise pressure gradients, and then deploy all of them together in very complex geometry. It's kind of like a possible vision to implement complex control strategies in very realistic geometries by using what we know from simple canonical cases. And this is a compilation of some additional reinforcement learning problems that we've been working on. We have this article last year in Nature Communications where we did a separation control. So basically, again, with reinforcement learning, we outperformed the classical periodic control for this problem. Paul, who was working on the wing, also worked on this one. These are 3D cylinders. As I increase the Reynolds number, the weight becomes more unstable, and the reinforcement learning algorithm can pick up the growing instabilities, leading to better performance at higher Reynolds numbers in terms of drag reduction. And we also have a heat transfer problem, a 3D relevant air convection scenario where Joel Bassant, actually he found something quite cool. This is the near wall heat transfer, the near wall temperature. And with the reinforcement learning, we found a completely new realignment of the convection cells, which reduced significantly the Nusselt number, so the convective heat transfer, leading to a stable configuration after turning off the control. So also for heat transfer problems, we found quite good performance. So I see quite a lot of potential for reinforcement learning and control. And many of these ideas with explainability, causality, feed into the second part of the talk on foundation model for discovery. So some of the initial work in this direction comes from this review paper that Steve and I had a few years ago in Nature Computational Science. This was a review on how ML can help CFD. And already at that time, I think there were some people looking at this, but I think this review kind of helped to guide some of the research that came the years after. Many people, for example, were focusing on this one, on trying to accelerate DNS. And we were not so sure that was a very, very promising direction, and not so much work was done after that. Improving modeling, so runs and LES models, there's quite some work on that direction, but we identified the reduced order model arena as the most promising one, and that effectively has been what people have been focusing on over the past 4 years. We have since then published a couple of years ago in Nature Communications a study on how to build effectively nonlinear POD with beta variation autoencoders and transformers in a way that the autoencoder would compress nonlinearly space and the transformer would model time. The key with the transformer, and we don't use a normal transformer, we use a particular type of transformer that captures the multi-scale interactions in turbulence, and that allows us to model the latent space in time quite well. So it's just a slide to kind of show a little bit what we did there. Once you use your beta VAE, your latent variables are basically, vectors, and then the transformer can reproduce that quite well. We actually did another thing where we trained both the autoencoder and the transformer together in a composite loss function that gave us pretty good performance in some cases. So there are some interesting ideas here. But I don't want to get too deep into this because the whole idea where we could extend these methods is to go towards foundation models. So potentially having many different data sets from many different geometries, in this case, different wings, different flows around urban environments. We could potentially design models taking advantage of generative AI. And again, the beta VAE framework can help in this regard. That we could, first of all, build a compact latent representation where all these different geometries can go together and can be analyzed together. And then we could use explainable AI, so these ideas with SHAP, to essentially connect any physical insight obtained in the latent space with physical quantities that we can understand in our physical space. And there is a whole idea here on how to generalize across geometries. We use a graph neural network, which basically takes geometries and it will create embeddings for those geometries to be able to essentially generalize quite well. I'll tell you more about it in the next slides, but basically we want to take from the existing cases a pretty good general approach to obtain data in new cases. So, and some details on this can be found in this review that we have with Steve and Gianmarco. So let's assume that we have one data set, which is 4-dimensional, in this case, 3D in space plus time. And if we use the beta VAE plus transformer framework, that's going to map into a 2D latent space, right? So this direction is space, and we'll have few latent variables, 5 to 10, maybe more, depending on the complexity of the system. And the second direction is time. This is the one that is modeled through the transformer. So 4D maps into 2D for one particular case, and then the decoder allows me to obtain the whole time series of snapshots once again back in the physical space. So this is what we did in 2014, nothing new here. But turns out that if I add more data sets, each of these data sets will map into a different plane of that latent space, such that potentially, well, I have a third direction, right? The third direction is going to be the flow case, meaning new geometry, new Reynolds number, new Mach number. You have a collection, a stack of 2D latent spaces, latent representations, forming a 3D latent space where this third direction is basically the flow condition. And what we did was to learn this distribution here with conditional latent diffusion. So basically, we use a diffusion model for these planes. So we are basically learning images, and you know how diffusion works with noise and then denoise. And the prior is obtained through a graph neural network that is identifying each of these geometries that you have here. So the conditional latent diffusion model is going to generate a new plane here in the latent space, a new 2D plane, based on the embedding corresponding to any new geometry that I introduced in my model. So if I want to do a wind turbine now, let's imagine, I will just encode that with my graph neural network, get the embedding. With conditional latent diffusion, I will create a new plane, so a new 2D representation for that new geometry, and then I need to decode it to visualize that in the physical space. Okay? And there are more details. You can read more in this paper. Actually, Abhijit and Frank Giral, two of my students, have been doing amazing work on this, since the last 8 years that we had some of these discussions. They have really done a lot of fantastic work, and there is this preprint that you can check out for more details. But essentially, we've been looking at two problems. One is this one where we want to not only generalize geometry, but we want to have an agentic framework that can do discovery for us, or at least help us in the discovery process. So this geometry is simple. It's basically two cylinders in tandem. We can change just the separation between the two cylinders. We run a total of 28 simulations where 40% are for testing. So those simulations are not used for training at all. This is an unsteady problem. So each of these geometries has its own temporal sequence, right? So we have about 5,000 snapshots, a few thousand snapshots for each of these geometries. And then the foundation model, what it needs to do is, well, we train it on the seen geometries and see how it performs for the unseen cases. So here at the top, I'm showing you the mean flow. Again, the foundation model is predicting snapshots, and then the statistics are calculated on those snapshots. And on the bottom, I'm showing you the stringwise velocity fluctuations. First row is the simulation, second row is the foundation model. And the first and second columns are new cases, but interpolated in the range of separations that we consider. The third column is extrapolated, so unseen and also beyond the range considered for a train. And you can see that for the mean and the fluctuations, the agreement is excellent. We are talking about 1% error or something like that. So we get a pretty good representation of the statistics. This is a very simple case, of course. But again, we have a model which generalizes pretty well to unseen geometries, which now we can potentially exploit or to do some exploration of this space. And that's where the agentic framework comes in. So what we wanted to do, this is again two cylinders in tandem. So we wanted to systematically and autonomously explore the wake recovery between the two cylinders. And the wake recovery, one way to look at it is looking at the displacement thickness and the momentum thickness. And so basically, at some point when the second cylinder hits, you will have again velocity deficit, but there will be one point where that those two quantities will be minimum. So we prompted basically with this agentic framework to find this curve, and this agentic framework automatically and by itself decided what cases to run. And running means generating a new geometry, decoding it, finding the snapshots in physical space, calculating the statistics, getting the point, and then looking at new geometries to kind of see how to build these curves. And this was built by itself by the agentic framework. The yellow line is the position of the minimum stringwise distance. So the stringwise distance of the minimum momentum thickness as a function of the separation between the cylinders. And the blue line is basically for the displacement thickness. There's a change of curvature which the agent could capture pretty well, actually. So the symbols are basically data from the high fidelity simulations. And of course, doing this, if we would ask a group of students to do this, that means that we'll have to remesh, rerun cases, calculate the statistics, decide the next case to run. Whereas in this case, we don't have to rerun any case. It was all purely based on the generalizability properties of the foundation model to new geometries, to new separation properties. So that was actually pretty cool. And of course, this is a simple form of discovery, but we have quite some ideas guiding causality, formal verification methods to try to have formalized scientific insight on new conditions and using explainability to connect that insight with physical mechanisms that we may be able to explain. One more example. This is on the iLib configuration, the CRM, where this was a pretty complete data set where Neil Ashton from NVIDIA and a few folks from Boeing presented it in SciTech earlier this year. This is this iLib configuration where there are a total of 1,700 cases modifying angle of attack and flap and slat angles, essentially. So a lot of possible cases. These are preliminary results, but we took 100 geometries and then we trained our model to try to see how the performance would look like in 15 different unseen cases, both interpolated and extrapolated beyond the training regimes, the training ranges. One note, once the model is trained, creating a new case, so 50 million points in a new geometry, unseen geometry, takes us less than 30 seconds on a single GPU. So these world model LESs, we're talking that they could take a day, 2 days, maybe. These are not super expensive, but costly simulations. Now for us, maintaining a very similar accuracy to that of the world model LES, it takes us 30 seconds. So for exploration, at least early exploration, this seems to be pretty promising. And this is the performance that we get. This is for a completely new geometry, but interpolated, so within the range of parameters explored in the training. On the left, you have this is the stringwise velocity, close to the airplane surface. On the left, you have the ground truth, which is the world model LES. And on the right, on the middle, you have the prediction from our foundation model. We get less than 4% error. So you can see that the distributions are actually pretty similar. We capture key features both behind the turbine towards the wingtip. I mean, we get a pretty good distribution of what the original data looked like at a much reduced cost. And if we look at an extrapolated geometry, so we have this case with this combination of angles, angle of attack and flap and slat angles. Once again, we get very good prediction of the velocity distribution, 5.4% error, and the pressure distribution gets us less than 1% error. So we get very good accuracy in completely new unseen geometries. So this is, I think, pretty exciting. It can really be a way to. So the first part about the two cylinders was more about scientific discovery and how to do that automatically. This part is a bit more about how can we have accelerated design loops in industry in terms of being able to generalize and automatically decide what cases need to be run for what purpose we have in our pipeline. And that's a summary of what I talked about today. We talked about the SHAP approach to identify important mechanisms in turbulence, but in other high-dimensional systems as well. Reinforcement learning as a way to reduce drag, and also combining SHAP and reinforcement learning to achieve even higher performance. And finally, I talked a bit about foundation models and agentic systems, which can be a revolution for scientific discovery and also design. Lots of the codes are available in this repository, so feel free to reach out. And yeah, that's what I have for today. Happy to take your questions.
I'm curious for your high lift aero ML dataset results. Is your surrogate predicting like a surface, like, or is it predicting the whole volume?
It's predicting the whole volume.
Okay.
Yeah.
So that's 5% error on the entire volume. Then.
Correct.
Okay.
Correct.
Yeah.
Locally, there are points of lower error and higher error, but the mean on the whole volume is 5%.
Okay. Thank you.
Yes.
Question. Would you be able to talk a little bit more about exactly like what the SHAP criteria is identifying and maybe how you can use that to correlate similar structures between very different flows that might exhibit similar dynamics? I guess I'm confused. So like if there's like a number and if you get above this threshold, that's now like a SHAP identified structure. Maybe I have a misunderstanding.
Yeah, no, I see what you mean. I mean, you're basically going the other way around, how different structures can compare with the SHAP in a way and in different geometries. So what we have seen is that actually, so we have done this SHAP analysis at much higher Reynolds numbers. And what is quite cool is if you look at the PDFs. So this is the PDF at ITAO 550. When we compare with ITAO 180, what we get is exactly the same curve cut here. And if we go to higher Reynolds numbers, what we get is the same curve up to this point and then extended beyond. So there is a quite interesting resemblance in the SHAP analysis going to different Reynolds numbers and going to other geometries. We've done this analysis on the NACA 4412. Actually, I don't have the results here, but we've done it also on the NACA 4412. And then the effect of the pressure gradient impacts what are the important structures and what are not, right? So then this distribution changes. The point is you can find some essential mechanisms across Reynolds numbers and across geometries, which can then be used later on for control. I can tell you one thing. This one, the reinforcement learning for SHAP, so these results are at ITAO 180. And then we took this model without any retrain, zero shot, and we went to ITAO 550. So with the SHAPs identified at 180 and the reinforcement learning trained for 180, and we got a bit worse performance than here, not much worse, and we completely killed opposition control at 550. So there is a certain transferability of these important structures, which also supports more our belief that these play important physical mechanisms in the system. That's what I was saying. More questions.
If there are any questions online, you can also write them in the chat because we can see them. If there are more questions here, if not, I want to ask one, and it's related with what Sam was saying. Have you used the Shapley values to improve turbulence modeling, like for closure modeling? And if so, how do you merge different regions?
That's an excellent question. So that's actually one thing that we're starting to do. We haven't done it, but we're starting to do. And the idea is, so there are systems. So think of very complex simulations because, at the end, if we're doing a channel flow, I know the statistics. I can, do a closure model based on the known statistics. But if I go to a completely new aircraft configuration, I don't have the statistics for that, right? Mm-hmm. But I want a model. So what if we would do the SHAP analysis for some quantity? It doesn't need to be the velocity. It can be lift and drag. Imagine that I want to have a turbulence model that predicts very well lift and drag. I could do the SHAP analysis for lift and drag, understand what are the important mechanisms for lift and drag, and then train a closure which is calculating those structures very well, and nothing else. But you could have an MSE that is weighted with very high weight on those structures and almost nothing everywhere else. But you're going to focus on your predictive power of your model on those mechanisms, which encapsulate whatever is important from your flow field for just lift and drag. So the idea is that you can basically have a causal modeling framework where you are assessing what's important and making sure that your models reproduce that and nothing else. Again, this is something that we are starting to work on, but that's kind of like one of the ideas. Yeah.
And maybe on the second part of the presentation, the agentic framework, it's very interesting, but I was wondering if what or how would you adapt it if you have like new physics? So for example, if you want to use same framework but for combustion, how would you do it? Like how would you include different physics within the entire framework?
Yeah, that's a very good question. This is in our roadmap. So we want to go to multi-physics, which I think is where most of the value comes here, because now I can have connections, causal relations across physics, across different physics, right? And one possibility is to have a fourth axis here, which is different physics. So combustion, chemistry, nuclear, multi-physics. Another idea is to explore other shapes for this latent space. I know there's some work with NVIDIA where they're looking at spherical latent spaces that can help you, then you have a natural periodicity there that allows you to wrap many more physical phenomena on that latent space. So this is very exploratory at the moment. And my guess is that the first thing to attempt would be to try a fourth axis with different physics and try to do causal analysis in that axis as well.
And if you were to add any experimental data within the loop, would it be like another box inside of like this left part?
It would be one more here. It would be at the same level. Mm-hmm. And then is where the whole work that you guys are doing on UQ and active learning, where that would come in. I mean, how does that compare with the other data sets, right? And well, in a way, the model would learn from the different sources, higher, lower fidelity. The experiments might give you a broader range of cases. Mm-hmm. So that could very well be also something that helps bring richness to the model.
Thank you.
Thanks for the questions.
So obviously here you said that implementing this even on a toy problem is a very good start. If you want to implement this on a more complex application, kind of like the ones you're highlighting there, what kind of magnitude of data would you need? Because we know that the transformers especially are quite data hungry, right? So have you explored that question, or do you have an insight?
Yeah, so I mean, we've been looking at this type of geometry, right, which is already quite complex. It's not a full scale, because at the end this is basically a wind tunnel model for a full aircraft, but still it has quite some geometrical complexity. So in this subset, using 100 cases, we found quite some generalization, and we're talking on the order of 100 million parameters for this model here. Maybe it's 300-400. It's that order of magnitude. So we are not going into the billions of parameters yet. The main idea, compared with much larger, LLMs and so on, is that we can encode quite efficiently this data by looking at the causal relations that are important for the system. So we don't blindly represent the data by increasing the size of our network, but rather by trying to incorporate the important physical mechanisms in our system. So yes, they're not huge. We're training maybe 4 GPUs, sometimes up to 8 GPUs, H200s, but it's not like, gigantic training tasks. It's more about thinking before training, I would say. Thinking how to design the latent space before training.
And another question on this, on the error, just following up. So here you said that on the entire volume, the mean was something like 5%, right?
Correct.
Was there a big discrepancy between the error across the wing and then across the fuselage?
There were points with maybe 40% error, 50% error, and there were many points with 0% error. So of course there is some discrepancy there, and that's because we haven't brought any weighting on where we want to focus on. Right? We're giving the same weight to everything. If now, because this was purely for data generation, if now we decide that we want to use this for lift and drag, then we probably give more weight to the information close to the surfaces, and then we will not care too much about the information farther away. But it was more meant as a proof of concept that we can generalize with reasonable accuracy. Yeah, thanks.
More questions?
It's about like what qualitatively these SHAP values or like SHAP structures rather look like. Like we know that qualitatively like streaks are something that are like very important in like boundary layer flow, for example. And if you have these SHAP structures that you identify across very different flows with very different physics, do they like manifest as different, like qualitatively different structures depending on what flow they're identified in? Or like, could there be categories of different interesting SHAP structures? Or is it less, I guess, specific?
That sounds like a great PhD topic.
Okay, great.
No, but I mean, we have, so far we have done SHAP on channel flows at different Reynolds numbers, and then we've done a couple of wings. So, I mean, of course, if you take the beginning of a wing where the pressure gradient is small, they look very similar to what you have in a channel flow. When you start to increase the average pressure gradient, then they start to look different. And actually, something interesting that I can say, if you look at Reynolds stresses or streaks, when you increase the average pressure gradient, because before doing SHAP, I was doing a lot of more classical analysis, right? There's essentially two things that happen with an average pressure gradient. One is that the stronger wall lunar velocity is pushing fluctuations away from the wall. So there is much more concentration of extractor farther away from the wall. And if you look at the geometrical properties, their inclination increases. So they suddenly become shorter and more elongated in Y. If you look at vortices or also Reynolds stresses. The same happens with SHAP. So some of the geometrical characteristics that you would expect from classical approaches, they're also reflected in the SHAP.
Cool. Thank you.
Yeah, thanks for the question.
We have one question online as well. Well, you can.
I was just thinking that we talked in the last meeting about variable fidelity modeling as well. It's just something that I'm interested in. I assume not all geometries are equally important in terms of like their ability to represent this shared latent space. And also you don't necessarily need to use this entire latent space to represent those flow physics, right? So is there any work in sort of changing maybe the size of this encoder-decoder network or changing from a diffusion model to something else to maybe have this adaptive like variable fidelity modeling approach?
That's an interesting idea. I think that one of the benefits, because we've done some tests on these ideas for design, is that with explainability, you can see what parts of the latent space are important for what parts of the optimization that you want to do. If you want to reduce drag, it turns out that this is the space that is most relevant for that output. And in that sense, one could try to connect it with the UQ and the active learning, enhance that part of the latent space because that's relevant for your optimization, probably adding more data there or trying to focus on more parameters on that particular type of phenomenon. So yeah, that's certainly stuff that can help let's say a purpose-driven foundation model, but that would be in the category of fine-tuning later.
Thank you.
Thanks for your question.
So one last question online. Han Yun asks, does your SHAP computation rely on subset-based expectation in the original Shapley definition? If so, how did you handle the computational cost?
Yeah, that's a very good question. So we don't do the original Shapley. The original Shapley computation is not feasible in these very high-dimensional cases. The Ariba 550 channel is on the order of 500 million points. So what we initially did kernel SHAP. And in kernel SHAP, you have a machinery that involves coalitions. So these are groups of structures And then you look at the role of each structure within those coalitions, which basically accelerates the process. You don't need to do everything as in the original Shapley formulation. And then a later development is a gradient SHAP, which is relying on integrated gradients and things along those lines, where you basically learn distributions and you exploit the gradients to calculate the SHAP. So that's, again, much more computationally efficient than the more traditional kernel SHAP approach. So these are methods that bring it to a possibility of computing this in high-dimensional systems. This is expensive, but it's doable. And we've always been quite careful in assessing the impact of any hyperparameters in these computational simplifications of the original number of structures per coalition, number of coalitions, number of fields for convergence. So we've obtained pretty robust results. But you're right. I mean, these are, let's say, computational simplifications of the original essence, of the original formulation, but they give pretty robust results.
Thank you. And I think we'll leave it here because it's already past 12:30. So just thank the speaker again for coming.
Thank you.